Hi ladies, this is lesson 8.3, and in this lesson we're going to look at areas of circles and regular polygons. So we've looked at areas already of some special quadrilaterals and triangles, but now we're going to recall the area of a circle as well as the perimeter of the circle. And then we're going to look at the area of regular polygons, and we're going to use these area formulas in order to solve some word problems. So first we have a vocab term, and that vocab term is apothem, and that's a perpendicular segment from the center of a regular polygon's circumscribed circle to a side of a regular polygon. Now you have to remember the words circumscribed and regular. So regular polygon means the polygon has all equal angles and all equal length sides. And the circumscribed circle is a circle that goes around the polygon and touches all the vertices. So in this figure, the circle is circumscribed above the polygon. So the next part of apothem is that it's a perpendicular segment from the center to one of the sides. So that segment, perpendicular, means 90-degree angle, and it goes from the center of the circle to the side of one of the polygons. So if you look at your note sheet, in figure 1, the question is which shape, the circle or the square, has a larger area, and which has the larger perimeter. So in the first figure, the circle is inscribed in the square, meaning the circle is inside the square. And in the second figure, the circle is circumscribed above the square, meaning the circle is outside of the square. So in a circumscribed circle, the circle touches the vertices. In an inscribed circle, the circle touches the sides. So in the first figure, the square has the larger area, the square has the larger perimeter, and the entire area of the circle is included in the area of a square. And then also the distance around the square is larger than the distance around the circle. So this tells us that the area is larger in the square. That was Liza. She's here helping me today. And this is describing the perimeter of the square that's larger than the circle, the distance around. So we can do the same thing with figure 2, which shape has the larger area and which shape has the larger perimeter. So in the circumscribed circle, the circle has the larger area and the larger perimeter because the distance around the circle is larger than the distance around the square. And secondly, the entire area of the square is included in the area of the circle. So in this next section, let's define the formula for the perimeter of a circle. And perimeter of a circle we call circumference. And the circumference of a circle is 2 times pi times r. And r stands for the radius of the circle. So that measures the distance around the circle. Now, to measure the distance or the area inside the circle, we use the formula pi r squared. And pi, we can estimate pi at 3.14. So pi is a number, it is not a variable. So let's look at this first example. It says the small pi is a diameter of 8 inches. So diameter measures the distance across the circle, if you remember from our circle unit, and it goes through the center. The diameter is 2 pi, or 2 times the radius. So the diameter is 8 inches, and the large cherry pie has a radius of 5 inches. So the cherry pie has a radius of 5 inches, and the small pie has a radius of 4 inches. So the diameter is 8, and the radius is 4. So the question is, how much larger is the larger pi? So we're looking at area here. So how much more pi is in the large cherry pie than in the small cherry pie? Small apple pie. So we'll have to do a few computations, and we're going to use the area formula to do that. So in the small pie, the area is pi times 4, which is the radius, squared. And we know the radius is 4 because the diameter is 8, and the radius is half of the diameter. So that means the area is 16 pi. And we're just going to leave pi in our answer. If we wanted an actual number, we could compute it. But we're going to end up with pi in both of these answers. So for now, we're just going to leave it there. In the large cherry pie, the area is pi times the radius, which in this case is 5 squared. So the area is 25 pi. So we can see that the area of the larger apple pie is 25 pi, and the area of the smaller apple pie is 16 pi. So if we look at how many actual square inches that is, we're going to multiply 16 by 3.14, and we get 50.24 inches squared. Of apple pie. And if we look at the cherry pie, 25 times 3.14 is 78.5 inches squared of cherry pie. Now the question is, how much larger? So we know it's larger, but the question is how much larger? So we're going to take the difference of the two. So 78.5 minus 50.24, and they're both in inches squared. We get 28.26 inches squared. So the cherry pie is 28.26 inches squared larger than the apple pie. Now in example 2, we're given the area of the circle and we want to find the circumference. So the area, we have an area formula, and that's pi r squared, and we have a circumference formula, and that's 2 pi r. So in both of these, we have radius. So we want to find the radius in order to find the circumference. So if the area of the circle is 256 pi meters squared, and that's equal to pi r squared, and divide both sides by pi, and we get 256 equals r squared. In order to solve for r, we have to take the square root of both sides. So now we have r equals the square root of 256. And the square root of 256 is 16. So we know that our radius is 16. So if we know our radius is 16, we can use that to solve for our circumference. Our circumference is 2 times pi times our radius. So our circumference is 32 pi. All right, now I want you to look at at your note sheet, and you have a few questions related to those regular polygons. If you look at those regular polygons in the pentagon, you can see that there are 5 triangles. In the hexagon, you can see that there are 6, and in the heptagon, you can see there are 7. So take a couple minutes. You can work with a partner if you'd like, or you can work individually, but write the area of the triangle in terms of altitude, A, and side, which is the base, S. So the area of the triangle, written in terms of A as an altitude, where A is the altitude and S is the base, the area of one triangle is 1/2 times the side times A, which is the altitude. So if the area of one of those triangles is 1/2 side times the altitude, then in a pentagon, since there are 5 triangles, it's 5 times 1/2 times the side of the altitude, or 5/2 times the side times the altitude. And so you'll repeat the same steps with a 6-sided and a 7-sided figure. And so in general, we can come up with this conjecture that says the area of a polygon is written by the formula 1/2 times a side, and this has to be a regular polygon, 1/2 times the side of one of those polygons times A, which A is the apothem. It goes from the center of the circumscribed circle to the side perpendicular to the side of one of the sides of the polygon, times the number of sides it has, or 1/2 times the perimeter times the apothem, because the perimeter is equal to the length of one of the sides times the number of sides in the polygon. So using that conjecture that we just came up with and what you know about area, so take a minute to read through this problem. You can pause the video while you do that. So in this problem, we need to find the area of the trampoline and the area of, so the trampoline is the octagon, the 8-sided figure, and then the area of the foam safety ring is the 12-sided figure that's around the outside of it. So we need to find the area of both of those. We're going to find the area of the 12-sided figure and subtract the area of the 8-sided figure in order to get the area of the foam that they are need to cover, or that they're going to need to cover around the trampoline. So we can use the formula that we just derived on the last section of our notes. And for an octagon, we know that the apothem is 10 feet, that each side is 8.2 feet, and that there are 8 sides total. And for the dodecahedron, we know that the apothem is 13 feet. We know that each side is 7 feet, and we know that there are 12 sides total. So to find the area of our octagon, we're going to take 1/2 of 8, that's 8.2, times 10. So the area of our octagon, the dark purple region, is 328 feet squared. Now we're going to apply the same formula with the dodecahedron. So we have 1/2 of 13 times 7 times 12. And we get a total of 546 feet squared. Now we don't need the whole area of the decagon, we just need the side outside of the trampoline. So we're going to subtract the area of the trampoline because we're not going to cover the trampoline in foam, we're only going to cover the outside area. So if we subtract 328 from there, we get 218, and that's how much foam padding we need. So there are some homework problems on page 422 to 424 for extra practice for you. So please, after watching this video, do those homework problems and come to class with any questions that you have. Thank you.